Let us look at this example right here. We're going to use the energy approach where we're going to find the velocity of the block at A and B. So if you notice, if we had chosen to use a kinematic approach, it would be pretty complicated because we would have to use summation of forces in A, summation of forces in B, do the accelerations and velocities. But now we're going to use the energy approach where we have the delta of U is equal to the change in energy from 2 to 1. And since the energy is conserved, we're going to find the um, energy transfer from one block to the other one through the rope, which is not elastic, it's a rigid rope. So the problem says the blocks, the boxes, are connected together by a cable, which is not elastic, it's a rigid cable. So this is the first thing, it doesn't have a spring, simplifies a lot. If the system is released from rest, so that tells us that the velocity of A, state 1, is equal to 0. So state 1 is going to be 0. Very useful to know that. They're asking determine the velocity of the block at A after it has moved for 2 meters. So the distance equals 2 meters. Since it's rigid, this distance is also going to be 2 meters. And they're telling us that the coefficient of friction between A, the block, and the ground is 0.25. So the coefficient of friction of A equals 0.25. Okay, and the pulley is frictionless, so there's no energy loss here, and all the energy here is going to be conserved here. If it was frictionless, it would just simply be a percentage of the total energy, but we don't have to worry about that. It's completely frictionless, which is an ideal case. All right, so let's look at the way to solve this. The first thing we need to know is that we're going to use the principle of work. So define your states. The first state is when velocity equals 0. The second state is when we have traveled 2 meters. So what's the velocity, what's the work, all those things can be found based on the equations. Now, the other thing we need to know is that, or the strategy, is going to be the two relationships are combined. So blocks A and B are going to be combined through equations, either by the distances or you choose how. In this case, the distance will be pretty straightforward, and also the velocity of A is the same as the velocity of B because the cable is basically like a rigid body. All right, so let's look at that. Let's start by block A. So in block A, we have the normal force, which is going to be very useful because we have a coefficient of friction. Remember, coefficient of friction at A is 0.25. It's pretty high. So it's quite friction. It has a lot of friction right here. All right. So the weight of the box is going to be vertically down, which is 200 kilograms. So that force is 200 kilograms times the acceleration, 9.8, etc. meters per second squared, right? Now we have this force that is pulling based on this weight, and then obviously we have the force of friction trying to go the opposite direction. The force of friction is the normal force times the coefficient of friction, right? We all know this from statics and from earlier problems in kinematics. So let's build the equations. That's the first thing we need to know how to do. So as we said, the weight is 200 kilograms per times the acceleration. So 200 times 9.81 equals 1962 newtons. That is 1962 newtons. So that's the first thing that it's given. In fact, you can do the same thing for block B, but we'll do it here in a few minutes. Now, the force at A, or the force of friction because of A, is going to be the normal times the coefficient of friction, as we said. And in this case, it's not, the plane is not inclined. We don't have cosine or sine or anything. It's just the same vertical force. So the normal force is going to be the same as the weight. Therefore, the force of friction is equal to the coefficient of friction times the weight. Okay, that tells us that is 490 newtons, is basically 1962 times 0.25. All right, so we have the two things that we would need from the force perspective. Fc, the force from the pulling, they call it Fc, but really is the Fb. But let's call it Fc, that's what they want to call it. In the this is from the book. The force from the cable, Fc, is the only one that we don't know quite yet. So if we set the equations, we know that delta U is equal to the energy from 2 minus the energy at 1. They like to keep signs positive, so T1 plus delta U, or U from 1 to 2, whichever you like best, is equal to the kinetic energy at point 2. But since the velocity is 0, then it's very convenient. Kinetic energy at 1 is 0. Okay, so the kinetic energy at 2, we don't know the velocity. It's one of the things that we need to know. So at T2, the kinetic energy at point 2 is 1/2 of the mass, which is 200 kilograms, because this is going to be in newtons, times the velocity final squared. We don't know that. So that's the first unknown, the velocity. So we know that our work, U, is equal to the force times the distance traveled. In this case, we don't want to do the continuous approach. We want to do the state approach from state 1 to state 2. So at state 1, we start from 0 meters. At state 2, we go to 2 meters. So the force is going to be the force of the cable times 2 meters. Okay. And if you go back to your equations, this is the same thing that we did with the car. So the car is moving forward because of the weight of the car, but there's a braking force that is making it lose energy. But both forces are present for the distance, right? For the 2 meters in this case. The way you set that up is like so. This is U from state 1 to state 2. So Fc times 2 meters minus, why minus? Because it's negative. It's going against the plane. It's making it lose force. Right right here, we're in a perspective of gaining or losing. So this Fc is positive, not only because it's on the right hand side, which that is not quite as important, is not respect to a coordinate system, is because this is making it gain energy, but Fa is making it lose energy. If Fa was lower, this distance would be higher at the same Fc. So make sure you understand the convention here. So Fc times 2 meters minus Fa times 2 meters, that's just U, this is this portion right here, is equal to T. All right, that's very simple. But we do know Fa, 490 newtons. So simply write the equation again. Fc times 2 meters minus 490 times 2 meters equals 1/2 of the mass, 200 kilograms, times velocity squared. All right, so we should only have one variable unknown, which is the velocity. Okay, so we have the first equation. Now, let's go ahead and do the second equation. For box B, we only have vertical forces, the force of the cable and the weight. The weight is mass times gravity. So this is 300 times 9.81. That is 2,940 newtons. There's no friction, there's nothing, the air friction is not considered, and it would be pretty small anyways. So we set up the same equation, delta U equals T2 minus T1. They're telling us that since this one started from 0, block A, then this one also started from 0. So T1 is going to be 0 because P1 equals 0. If the cable wasn't rigid, the only difference is that this will not be traveling 2 meters. It will be traveling some distance from the elastic behavior of the cable. Therefore, what we need to do next is use the same equation, now taking into consideration the 2 meters. So we're going to do the same thing. The cable traveled 2 meters, so the force of the cable times the 2 meters, because we need to get the work done, which is force times distance. Okay, so remember, work is force times distance. This is the force of the cable, and the distance, we have newtons of joule. We have units of joules. This is in newtons, and this is in meters. Newtons per meter is joules. And then on the other hand, we have the same situation, but from the weight of the box at B, the second box, this one. We did the same for A, now we're doing it for B. So it's going to be 2,940 newtons times 2, like so, and equals to the kinetic energy at point 2, which is 1/2 of the mass of at B, which is 300, and the velocity squared. Now, since, again, the cable is rigid, the velocity of box A and the velocity of box B are moving at the same speed, even though from kinematics, one is in one direction and the other at B, the box at B is moving in a different direction, the magnitude is the same. And here in an energy approach, we don't care about the direction, we care about the energy. So the velocity is the same. Given that they're the same, we're gonna combine these equations using the same variable. So notice we have two equations, two unknowns, Fc, which is the force of the cable, and the velocity. So if we need to find the velocity, we're just going to substitute the force of the cable. That's what we're going to do. The equation number 1 is Fc is making it gain energy. So we're going to keep that positive. And in the second one, since is with respect to gravity, remember that this is a potential energy case. If the box was falling by itself, it would be a potential energy case, but the force of the cable is holding it from falling like with gravity. So this is going to be subtracting energy, trying to avoid a free fall. The force is negative. Okay, does that make sense? It should, right? This is the weight times the mass. This is the mass times gravity, which is the weight at B. And this is the force of the cable. With no force of the cable, this will be gaining, this is a potential energy, and it will be falling. So Fc is the energy needed to keep it from falling. So we're going to subtract Fc. All right, and bring the rest of the equation down. This is just substituting equations, and once you do that, you simply solve for V, and it gives you a 4.43 meters per second answer. So go ahead and solve your equation, and you're going to have this answer.